All right, in the last portion of today's lecture, we're going to apply some of the ideas we learned about for amortized variational inference to actually describe some real neural network models that we might want to use in practice. So the first one that I'm going to cover, which is the most directly based on the material that I presented, is the Variational Autoencoder. The Variational Autoencoder is a generative model over some variable x. Oftentimes it's used to model images, in which case x is a representation of an image. So in a Variational Autoencoder, there are observed variables x, and there are latent variables z. And q phi of z given x is given by a Gaussian distribution with a mean mu phi of x and variance sigma phi of x. And then the decoder, or the generative model, p theta of x given z, is also a Gaussian with mean mu theta of z and variance sigma theta of z. Now remember, in the beginning of the lecture, we talked about how in a latent variable model, it's pretty typical to have a simple distribution over z and a simple conditional distribution over x given z. But when you integrate out z, you can represent a very complex distribution over x. And that's exactly what makes the variational autoencoder work well. So in a variational autoencoder, if you want to sample, you would sample from your Gaussian, typically zero mean unit variance prior over z, and then decode that z, that's the term used to sample from p theta of x given z. Here are some examples of a variational autoencoder that was trained to model people's faces. So here the x's correspond to faces, the z's correspond to a normally distributed latent vector. So obviously the distribution over faces is not Gaussian, at least the marginal is not Gaussian, but the conditional given x is Gaussian, and it turns out that you can model very complex distributions if you integrate out z. So the architecture for a variational autoencoder is precisely the architecture that I had in the previous section. The encoder Q, which is our inference network, takes in xi and produces the mean and variance over z. And then if we want to construct that z, what we would typically do is use the reparameterization trick, sampling from a zero mean unit variance Gaussian, take the mean, add epsilon times sigma, and that gets a z. And the z we can feed into the decoder to get back x. If you want to generate a sample, then you wouldn't use the encoder, you would just sample z from the prior, which is typically a zero mean unit variance Gaussian, and then decode that prior. So the objective for training the variational autoencoder is to maximize the evidence lower bound, the variational lower bound, with respect to theta and phi, and that consists of two terms. The reconstruction term, which is log p theta of xi given the encoding of xi, minus the scale divergence between the inference network and the prior p of z, where the scale divergence can be expressed as a closed form equation because both q phi of z given x and p of z are Gaussians, and the scale divergence of two Gaussians has an analytic form. All right, so how can we use the variational autoencoder? Well, we can sample from it. We can also evaluate the probability of a particular image x. So sampling requires just generating a sample of z from the prior, which is very easy because the prior is typically a zero mean unit variance Gaussian, and then generating a sample from the corresponding decoder p of x given z. Why does this work? Well, when we train the encoder and the decoder, intuitively, if you examine the form of the subjective, we have one term that basically says we should accurately reconstruct the image from z, that's the first term, and the second term says that encodings of an image should be close to the prior. So intuitively, the reason this works is that when you train the variational autoencoder, you're essentially training the decoder so that it decodes samples that are close to the prior into valid images. And the reason that the encoder produces samples that are close to the prior is because of the scale divergence term. So basically, the encoder pays a very heavy price if it encodes x's into z's that are far from the prior p of z. All right, now we can also use this idea to build conditional models. So conditional models would be models that generate some other variable y given x, but have an additional latent variable z. So what I have written out here is a particular instance of a variational lower bound for a conditional model. There are many choices to be made here, and this is just one of those choices. So here my inference network Q gives z condition on xi and yi, and then my generative model has a log p theta of yi given xi comma z, and a prior p of z given xi. Now the prior doesn't have to depend on xi, but it could. So here is a model where the prior doesn't depend on xi. So in this model, I would have just an unconditional p of z and a decoder p of y given x comma z if I want, for example, multimodal imitation learning. But generally everything is basically the same, only now we're generating y and conditioning everything on x. Of course, it's up to us as to whether we make the prior depend on x or not. We also don't have to make the inference network depend on x. In fact, the inference network is a valid lower bound regardless of what it depends on, although it is typically a tighter lower bound if it can match the posterior more accurately. So the graphical model for this scheme would look something like this. You have your inference network, which takes in xi and yi, and it produces the mean and variance over z. Just like before, we use the reparameterization trick, sampling epsilon from a zero mean unit variance Gaussian and combining it together to get z. And then z is fed into another network that takes in both z and xi and produces a distribution over y. And then at test time, we sample z from p of z, or p of z given xi if it depends on xi, and then sample y from the decoder. Here are some more examples of interesting latent variables. So in this paper called Embed to Control, which I showed before, so this is this illustration. Here they actually use a model that is similar to a variational autoencoder, only it is modeling sequence level information. So here z is not just a single vector, it's actually an entire time series, and the distribution p of z has a factorization in time into an initial distribution and a dynamics term. So the general scheme, and this is basically a recap from the model-based RL lecture, was to collect some data, learn embedding of images and dynamics jointly, and then, in the case of this paper, run an MPC algorithm to reach the goal. So the model here can be visualized like this. So it's a more complex model than before. Here the latent state is x, and there's a little bit of notational confusion because before the latent state was z and x was the observation. Now here x is actually the latent state and the observation is O. There are additionally these variables u, which we're not going to model, we're not going to generate u's, but we will condition on them. So those are our actions. But it's just a type of variational autoencoder with temporally decomposed latent state. So the equations for it are a little more complex, but they can be derived just the same as before from the variational lower bound. I won't go through this in detail, but this would be a good exercise to try to derive the variational lower bound for the sequence level model. We can also have local models with images, so we can have more complex latent variable models. This is also a paper that I mentioned in the advanced model-based RL lecture called Solar. And here, the model is a little bit more complex. There's actually a prior on the dynamics between the x's, which says that they should be locally linear, and some additional terms to model the costs. But the high-level idea is the same. We're still going to use amortized variational inference to capture the posterior, the distribution over x's given the observations that we have, and then we'll have the evidence lower bound, which will maximize with respect to both the encoder and the decoder. And we'll see a lot more variational inference when we talk about inverse reinforcement learning, so that we'll do next week. And then we already saw some models that used variational inference in the exploration lectures, so hopefully with the material that we covered today, those will be a little bit easier to understand.